Imagine you are at the gym. You're hanging out at the gym, but you got there at a really bad time because there's this big beefy bodybuilder, and you know what? He just got told his membership is revoked because he's never wiping down his sweat off all the equipment, and he's mad. He's so mad, he takes the door and he rips the door off. And he takes the door and he slams it. Actually, he throws it. He rips it off the hinge. Here's the door, and he throws it. He doesn't know where he's throwing it, but he ends up throwing it straight at you at a speed, we'll call it VD. You're looking at this door coming towards you. What do? I'm not ashamed to say I might start screaming. I'm like, oh no. I start screaming at a certain frequency. I'm going to call that frequency F. I'll call it, I was going to call it F me. That might be what I'm saying, but I'm going to say F of the scream. All right, so my question is, here's the thing. This sound is going to come over to here. It's going to reflect off the door. Then it's going to come back towards you. What sound would you hear after this sound wave reflected off the door and got back to you? Would you hear the same frequency that you're screaming at? Would you hear a higher frequency? Would you hear a lower frequency? Exactly what frequency would you hear? Let's figure it out. It's a good problem. It's tricky. All right, so I want to know what frequency would I hear? So I'm going to have to use the Doppler effect formulas because we've got some moving stuff going on here. So the frequency that I hear, I'm going to have to do this in 2 steps actually. First of all, the sound gets over here to the door. I'm going to think of the door as an observer first. This door is going to act as a moving observer. It's going to hear. I want to know what sound this door would hear if it was moving this way. Now, doors can't hear anything, but if this door was a person, what frequency would it hear? It wouldn't be F scream. It'd be something else. So I'm going to call this F door because I want to know what the door hears. And if we use the Doppler effect formula, F door is going to equal the frequency that the wave actually has, so frequency of the scream, maybe it's a yell, but it's scream, okay, times, over here, I've got this factor of, it's the speed of sound up top, and then it's plus or minus, for a moving observer, the formula was plus or minus speed of the observer, and my door is the observer here. I'm pretending like my door can observe. I want to know what frequency it receives, that it hears, divided by the speed of sound. Now I have to decide whether I want the plus or the minus. So I ask myself this. I can never remember this as a student. I always forget. There's too many plus and minuses here. And I'd say to myself, if I'm moving toward the source, or if the source is moving toward me, I know that means frequency that I hear goes up. So the frequency this door experiences should be bigger than the frequency that's actually emitted by the person over here, by me. So if I want it to be bigger, I want to have plus on top. I want a big numerator. So I'm going to erase that. I want the plus sign because a big numerator gives me a larger frequency. That's the way I remember whether I should add or subtract up here. All right, so now I'm not done yet. You might think we're done. If that's the frequency the door hears, well, that just reflects off the door, and then I should hear that frequency too. But no, because this is the frequency the door hears, but now the door re-radiates that sound back at you. This door is acting like a speaker, and it's acting like a moving speaker because the door's moving. And we know what happens with moving speakers. There's another Doppler shift. So there's 2 Doppler shifts that go on here. One, by the fact that this door is observing, experiencing a higher frequency. Then when it re-radiates that sound outward, when it reflects that sound outward, it acts as a moving speaker. We've got to do another calculation. Now, if I want to know the frequency, I'm going to use a different color so we can keep this all together. If I want to know the frequency that I will actually hear, so what frequency, when it gets back to me, what frequency will I actually hear? All right, we've got to do another Doppler shift. Here we go. The frequency I hear will be, all right, the frequency that the speaker was trying to radiate, which was this. Remember, this was the frequency the door was receiving. This was the frequency right here, F door. So it's going to be that times another shift. So let me just rewrite this over here. I'm going to have F scream times this factor that we had speed of sound plus speed that the door was thrown by the beefy guy over speed of sound, but times, I need to multiply this by another factor. You need to multiply this by another factor that takes into account the Doppler shift from the fact that the speaker, this door is not a speaker, but it's acting as a moving speaker because it's moving, the fact that this door is moving. And that looks like this. That factor, if you remember, speed of sound on top, and then on the bottom, it's speed of sound plus or minus the speed of the actual speaker, which is the door here. So I'm going to put VD. Now again, we have to pick plus or minus. Well, same thing. I go through the same thought process. The only thing I like memorizing is the fact that if things come toward each other, the frequency should be increasing. So again, speaker, this door, moving toward me, the Doppler shift should increase the frequency that I hear. So to increase the frequency, let's see, this is the denominator here. If I want to increase the total amount of frequency, I need to make the denominator smaller. So it seems weird, but I need to have a negative sign down here. I want to subtract. And I want to subtract because subtracting gives me a smaller denominator. Dividing by a smaller denominator gives me a larger total amount. And I know that I should be getting a larger total amount for the frequency I hear because the frequency should get increased by this Doppler shift. So this is it. This is the frequency that I would hear. I would hear a frequency of the amount I scream times these two factors, because there's two Doppler shifts happening here, and you can clean things up if you want. You can cancel off these VS's if you wanted to, which is fine, but the important thing is that there's two Doppler shifts. And you might think, well, this is just stupid. I mean, this was a really stupid example. When am I ever going to find myself in a gym and some beefy bodybuilder throws a door at me? Well, it is kind of stupid, but here's a real-life example. Instead of a door, imagine this is blood flowing. And no, the bodybuilder didn't like explode or something. Imagine instead of a gym, this is a vein or the inside of your body somewhere. And instead of me screaming like a girl over here, this is some sensitive piece of equipment. Sensitive piece of equipment that wants to image, that wants to scan the blood flow and know how fast is the blood flowing. Well, here's a way to do it. You send sound waves in. Those sound waves reflect off of moving objects, come back at you. If you can tell how much the frequency changed, you know this is dependent on the speed of the thing that was moving. So this, I called it speed of door, but in this case it would be the speed of the blood. You could figure out how fast that blood's flowing in there, and that's useful. Or if you're not a doctor and you wanted to know, if you're a police officer and there's a car chase, there's a car heading towards you, you want to know how fast it goes. This car is coming toward you at some speed, and you want to know how fast it's going. You could be parked over here. You could use radar, shoot that radar. It wouldn't be sound. This time it's electromagnetic waves. This radar would hit the car. It would bounce back at you. That frequency would shift. It would shift by a certain amount that depends on the speed of the car. And this is how they can figure out how fast you're going and maybe give you a ticket. So slow down out there. Make sure you don't get caught by the radar. All right, so this is an application of Doppler effect.